Okay, so here we are looking at the second part of this worksheet. These are the longer answer questions. So the first one over here, simple harmonic motion in waves. A particle of mass m is attached to a light spring. Light spring is basically giving you the idea that you don't have to take the mass of the spring into consideration. Is executing simple harmonic motion in a horizontal direction. State the condition relating to the net force acting on a particle that is necessary for it to execute simple harmonic motion. Okay, now we know that the defining equation is minus omega squared x, and because F is equal to ma, we have something like that. So what behaves with the A behaves with the force also. So the force is proportional to the x, and the force is always directed to the equilibrium, because it's always in the opposite direction to the motion, to the displacement at any specific time. Okay, so it's always important to go back to your defining equation, work from there. Next part over here, the graph shows how the kinetic energy Ek of a particle in A varies with displacement x of the particle from the equilibrium. So using the axis above, sketch a graph to show how the potential energy of the particle varies. So basically what happens is at this point over here, this is where you're getting maximum kinetic energy, you actually got zero potential energy. This is at a point at your equilibrium. And conversely, when you have zero kinetic energy, you're having your maximum potential energy. So you're going to have those points, and then you're going to have to draw a nice smooth curve, basically the reflection of this one, if you can draw that, something like that. Needs to be reasonably smooth. This is not so good over here at the base. This should be more like that, because the vertex or the minimum point should be the zero. Hopefully you will draw a better graph than me. Good. So going down to the next page here, we've got this over here. The mass of the particle is 0.3 kilograms. Use the data from the graph to show the frequency f of the oscillations is 2 hertz. So with this one over here, firstly we need to think of what formula we're going to use. Well, obviously the graph was looking at the energy, so we would want to use our energy graph. Let's just go back to the graph and see what information will be useful. So if I just go back up there here, we see that we've got a maximum kinetic energy here in joules of 0.06. So that's going to be important. So our maximum kinetic energy is 0.06. So let's go back down here. It's a bit more difficult for me than for you moving around here. So we've got a Ek max is equal to 0.06 joules. And then if I go to my formula booklet, I'm going to have to close this down. Going here, obviously from here we're going to be able to use this formula over here to relate the two. So bring that back again, back to over there. So we got 0.06 joules is your Ek max. You get told that your frequency is equal to 2 hertz. From that you can work out your omega. Now we have our formula Ek is equal to a half m omega squared x squared, like that. We're going to put that into, if we put our formula that omega is equal to 2 pi f, we can write this as Ek is equal to 1/2 m. Omega is going to be 4 pi squared f squared, 4 pi squared, and then we're going to still have an x squared, and we can, from that we can calculate our frequency. So we can have 0.06 is equal to 1/2 the mass is 0.3, 4 pi squared f squared, and we're going to have our x value, and our x value we can also take from our graph. If you look in the graph, that is 0.05 squared, and so we solve for f. Hopefully you'll be able to do that, and you should get your f coming out as 2 hertz, like that. Sorry, there should be an h there. Okay, yeah, that shouldn't be a problem, I think, for you to change that around. It's pretty straightforward. See if you can do that. For C, the particles of a medium M through which a transverse wave is traveling oscillate with the same frequency as amplitude as that of particle B. So we're looking at a transverse wave. Describe with reference the propagation of energy through the medium. What is meant by a transverse wave? Okay, so in a transverse wave we have the oscillation. I think I'm just going to read this to you and not write this out. We're going to have the oscillation of the particles in the medium are going at right angles to the direction of propagation of the energy, or the propagation of the wave itself. So the wave will move, for instance, in that direction, and that will be the direction of the energy, and your particles are going to move at right angles. These over here will be your particles moving at right angles to the propagation of that energy. Okay, next one, we got the speed of the wave is 0.8 meters per second. Calculate the wavelength. Well, we would use our formula that velocity is equal to frequency times wavelength. We're going to get our wavelength, therefore, is equal to our velocity over our frequency. We have our velocity is 0.8 meters per second, and our frequency is 2. So we're going to get 0.4 meters. Divide that will give us our wavelength. Good. Does that make sense? I hope that all makes sense. Going on to the next question here. Alright, so we have the diagram shows the wave fronts of a wave in C incident on a boundary XY from medium M1 to M2. The angle between the norm and the direction of the wave is 30 degrees. So here's your normal over here. Now these are your wave fronts. Those moving, the waves are moving in that direction over there. This over here would be your wavelength there, and they are going into a different medium, another medium M2. So it says over here the speed of the wave in M1 is 0.8 meters per second, and the speed is in M2 is 1.2. So the velocity has actually increased. So calculate the angle between the direction of travel of the wavefront in M2 and the normal. So we're going to use Snell's law here, where we get N1 over N2 is equal to the sine of theta 2 over the sine of theta 1, which is equal to V2 over V1. So we're obviously going to use this part of the formula here because we're not told anything about the refractive index. We're not sure that we're dealing with light in this case. So we got the sine of theta 2 is actually the one that we're actually going to be working. This wave is going to do something like that. It's going to move in that direction. There's going to be an increase in that because it speeds up. We'll talk about that in the next question actually, but we're going to have the sine of theta 2 over the sine of theta 1. So the sine of theta 1 is the sine of 30, which is equal to V2. V2 is 1.2 over 0.8. So we're going to get the sine of theta 2 is equal to 0.5, because the sine of 30 is equal to 0.5 times 1.2 over 0.8, and we can just do that on our calculators and work that out. So we're going to get 1.2 divided by 0.8 is equal to 1.5 times by 0.5. We get 0.75, so the sine of theta 2 is equal to 0.75, and then we're going to do the second function, sine of our answer, and we get it's about 48.59. Theta 2, this angle over here, theta 2 is about 48. I'll just write it out, 0.59. Now you see here that we are working to two significant figures here, two significant figures, so I would actually say this is going to be 49 degrees, that the angle will be. And then the next part of the question over here says, on the diagram sketch the wavefronts in M2. So now this, as you don't have to use a protractor or anything, but you need to be, if I go direct, it needs to be reasonably realistic. So if I go directly across, that would be what they are, but they would be doing something, your waves are now moving like that. Now what happens is that these waves, the waves over here, as they go through, actually speed up. So that will become like this. For instance, this is at 90 degrees, so that's it to be like that. That will be like that, and this will be like also like that. So you'd have your new waves are being formed like this. You can see here that you've got an increase in your wavelength. Your wavelength here, if this was your wavelength 1, wavelength 1, wavelength 2, wavelength 2 is greater than wavelength 1 because your speed is increased. Remember, the frequency is constant. Frequency is constant. Your wavelength increases because your velocity has increased. Okay. All right, thank you.